So hello again everyone. Up to now we have discussed about how does the alpha particle and beta particle manages to get out of this nucleus, and we see the alpha and beta particle decay from an unstable nucleus. We have also defined how does the neutron proton ratio defines the stability of the nucleus. So now what we are going to do is we are going to understand some of the basic terms that we keep on listening when we talk about radioactivity, and we have already learned that in our plus two uh, grade, but now I'm just revising it so that it would not create any problem in the following lecture. So let's understand these. Okay, the first thing that I want to revise is decay equation. And when we talk about decay equation, I think we all know and we all remember this beautiful equation, which is n equals n naught e to the power minus lambda t, where n stands for number of undecayed nuclei or atoms, and this n naught is the original number of nuclei or atoms. Okay, where and this lambda is something that we call as a uh, rate of not rate, but lambda here stands for, I think, decay constant. Yes, decay constant, and this t is the time period, or yes, the time period for taken for the decay. So now one thing that you might be interested to know about, or sometimes get confused, is number of undecayed nuclei. So why am I saying this to be a undecayed nuclei or atoms? Because we are just taking a sample of a radioactive element, and we, by using Avogadro's number, we can know the number of original atoms in that element, and that means this is also equal to the number of original nuclei before any kind of radioactive process. So we can understand this, and we can say this to be a nuclei or atoms, because we are just taking a sample element and we're talking about the original atoms, and that means original nuclei. Okay, so this is what we know as decay equation. Now let's talk about another parameter, or another uh, term, that is decay constant. Okay, lambda, which is decay constant. Now, when we say a decay constant, we already know from the decay equation that n equals n naught e to the power minus lambda t. So, if we want to get the expression for lambda, then what we can do is we can operate log on both sides, and that gives us product of this n naught and e to the power minus lambda t inside the logarithm. And if we operate it using the properties of log, then what we can get is ln of n naught plus ln of e to the power minus lambda t. Now this gives us ln n minus ln n naught equals minus lambda t, and if I just use this minus sign, or I just take minus and multiply it on the both side, then what I would get is ln of n naught minus ln of n equals lambda t, and that gives us n naught by n equals lambda t. Ln of n naught by n equals lambda t. Again, if I want to get the value of lambda, then I can get it to be n naught by n by e. Okay, so this is what the expression of our decay constant lambda looks like. Now, what does this expression say us? So we have uh, lambda in logarithm. right? Logarithm of n naught by n by t. Now, if you see this, you may wonder, you may get into a confusion of thinking that lambda is in logarithm function, right? And you already know that the logarithm functions has a graph which looks like this, which first increases and get to that maximum. Then I think you might have a confusion that this lambda, this graph represent lambda, right? That means you may also consider that this lambda is actually changing over time. That's why it's not a constant. It's not a constant. So why are we saying this to be a decay constant? If you are thinking in this way, then actually the approach that we are using in this is actually wrong, because lambda is a constant and lambda is equal for equal or just constant throughout the process of radioactive decay. Now let's see how. Now let's see that lambda is equals ln of n naught by n, n naught by n, n naught by n by t. Now it doesn't mean, so if you see this logarithm, doesn't think, you should don't think that this logarithm is a function, and that's why we have to use it, and we have to follow that graph you already mentioned. Actually, what logarithm here does is it just scales this n naught by n parameter into some other. You can think of it as the coordinate transform. So it's just changing its coordinates, how we see it, but it's not a function. So that means it's still a constant, and time is always constant. That's why lambda as a whole is a constant. So if you see the graph between t and lambda, it looks something like this, because it keeps being constant along the journey of radioactive decay. So this is what the decay constant is. Now let's see, are there any other terms that we need to talk about? And I think we have one, and that is half-life. Half-life. So let's see what half-life is. Now what half-life is? Half-life is actually a time where this initial number of atoms or nuclei get reduced, get reduced to the half of original number. That means this n becomes n naught by 2. And if it is n naught by 2, then what you can say is it is n naught by n naught by 2, and that gives us ln of 2 by t. And we want to find out the expression for half-life, so we can just hang a subscript there, half, and we can take t half is equals to ln2 by lambda. So this is what the expression of uh, half-life is. So this is half-life. Now let's talk about the units of radioactivity. Now when we talk about units of radioactivity, we all know one of the units is becquerel, denoted by BQ, okay, and 1 BQ is equals to 1 disintegration per second. So, okay, so this is what disintegration per second. This is a becquerel, 1 becquerel. Another is Rutherford, which is denoted by RD, and it is 1 RD 10 to the power 6 becquerel. Okay, so not okay. Yes, it is. Yes, it is. Then after we have Curie, which is denoted by CI, and this QD 1Ci is equals to 3.7 into 10 to the power 10 disintegration per second. Okay, so 1 QD is sorry, yes it is. So we can actually raise disintegration per second. So 1 to the power 10 to the power 6 disintegration per second, and QD is 3.7 into the power 10 disintegration per second. So these are some of the units of radioactivity. Now let's talk about some of the radioactive series. So talk about radioactive series. What is a radioactive series? Let's talk about this. When we say a radioactive series, it's sometimes also called as a decay chain, and it involves the radioactive. I think I should write it. So radioactive decay of parent nuclei into unstable into an unstable daughter nuclei and radioactive decay of that daughter nuclei into granddaughter nuclei until stability is obtained. This is what we call as decay chain or radioactive series. Now there are four major radioactive series. Since alpha particle is the only one particle that could change the value, and the value and value I mean value by value I mean the atomic number. So that's why we have four type of radioactive series, and among that four and these four type of series are actually uh, described on the basis of the reminder that are left. So we have four major radioactive series. Let's write them out. First one is thorium series. Second one is neptunium series. Third one is uranium series, and fourth one is actually actinium series. Actinium series, and these all are classified or divided on the basis of 4n plus 1 or 4n plus r, that is on the basis of reminders. Okay, four major radioactive series. Now let's talk about each of them in more detail. So let's talk about the thorium series, and we know thorium is 232Th90, where 232 is its atomic mass, atomic weight, and 90 is its atomic number. So this thorium goes under successive radioactive transformation, and it ultimately gives a stable nuclei, which is 208 Pb82, which is lead. And if you see this reaction, I have just clumped everything inside a single equation, but actually it's a series of radioactive transformations from one of the element to the another until it reaches to this most stable state or most stable element. So if you see here, the change in the atomic mass is 24, and we know If an alpha particle is 2He4, then we have to divide this by 4 to get the number of alpha particles. And we got to know that we actually 6 alpha particles are need to be ejected or decayed to get this stable configuration. But what about this uh, change in or decrease or increase in the atomic number? And to understand that, we need to track the we need to track the number of protons and neutrons. Now, since we have seen in this alpha decay, the proton decreased in the nucleus, right? That's why the nucleus become much more neutron rich. And for balancing that, what neutrons do is neutrons change themselves to the protons, and this is the chemical reaction. So this is a reaction that says that if neutron changes into proton, it would emit beta negative and a positron neutrino. So this is okay. So this is the how and what are the other things that are produced when the neutrons are converted to the protons. And if you see the total change in number of protons, then you can understand this by knowing that a thorium has originally 90 electrons or protons in its nucleus, and we can see the 6 alpha particle has been ejected. It means the 6 alpha particles must have 12 electrons with them or 12 protons with them. That's why it has to eject 12 protons. That means we have we have to have got 78 of the atomic number or number of protons. But we have got 82 number of protons in lead. And so what is this difference in between say 82 and 78? It's 4, right? So what is this 4? Actually, this 4 is the number of beta negative decays that happened in the series. So we have got to know that in this series, 6 of the alpha particles, 6 of alpha particles and 4 of the beta negative particles are actually decayed to give 232 thorium 90 into a stable configuration of 208 PV 82. This is what the gist of thorium series is. Now this thorium series thorium is the is the longest lived series. Okay, this is also known as the longest lived series. And so after this, okay, yes, so okay, it is it. So this is it. Now after this, let's talk about Neptunium series. Similarly, we get these facts for the Neptunium series. Now we can calculate for other two series, which are uranium and actinium, in the similar manner, and that we will do in the next video. We are continuing the lecture series on radioactivity. Now let's talk about uranium series. So uranium series is 238 uranium 92, and when it goes under the successive radioactive transformation, it will give us lead, which is 206 lead 82. Now, even though it is just shown in a single reaction, it's actually a series of reactions, and the series of reactions are not stopped until a stable nuclei is formed or until a stable nuclei is obtained. Okay, so this is about the uranium series. And if you want to know how many of the alpha rays and how many of the beta rays are there, then you can consider this. So if you see this, you would see, so what I did is I subtracted the values of uranium, the atomic weight of 238 uranium and 206 of lead, and then I get 32, and if I divide it by 4, it gives us 8. So this value 8 represents alpha, number of alpha decays. So there are altogether 8 alpha decays. And if you talk about the reduction in the atomic
number, or sorry, reduction in the number of protons because of this 8 alpha decays, it would result into 8 minus 2 equals 76 of the 76 protons. But we have 82 protons in lead. That means some of the electrons have been created in that reaction, in that series of reaction. And if we drag that, we would find out that there are 6 beta minus decays that are responsible for adding this adding 6 protons to that. Yes, to 6 proton to that element, that nuclei, and as a result of which the 206 lead 82 is found. Okay, is obtained as a stable product. So this is about the uranium series. And one thing you would like to understand, and I would like to know about the uranium series, is that it is most common kind of radioactive series that we see in nature. So this is it. Now let's talk about last of the series, that is actinium series. Okay, so let's talk about actinium series. Now, when I say actinium, you would be quite surprised to see uranium there, but don't be surprised. The name of this series, actinium, is based on the fact that it was found that in this series, the first of the member is actinium. So that's why it's so the name is justified. So here we are talking about not uranium 238, but uranium 235, and when it goes into successive radioactive transformation, it will give us lead, which is Pb 207. So previously we had 206, right? But here we have 207 and 82 lead. Now, so we can say that this lead and the lead that we are talking about, 208 one, so these are isotope of each other, and uranium, and we are also talking about the another isotope of uranium also. Okay, so this is about the series. This is about the I guess this is about the first product and end product. Now let's see how many of the atomic number yes no yes atomic weight has been changed. And if you want to calculate that, you would be interested in the subtraction, and that would give us 35 minus 7. So it would be 15. 15 means 9. Yes, 9 plus 5, 16, so 8. 8 plus 5, 15, so 8. 2, so 28. I think it is 28 plus 7 would be 7. 35. Yep, it is correct. So we have 28. And if I divide 28 by 4, I will get 7. So we have got 7 alpha decays. And as a result of this 7 alpha decays, we would assume that we had 14 of the protons has been changed into neutrons. Yes, that means we have a neutron rich nuclei, and as a result of which the neutrons are again changed into protons, and that means we are also getting some beta decays. And to know the amount of, or the number of beta decays, we would like we would like to subtract this 92 and from 14, and it would give us uh, okay, 4, 6, 20, and 76. Now 76 minus 80, so 82 minus 76 would give us 6. So 6 is the number of beta minus decays. So that's why as the overall conclusion we have got 7 alpha decays and 6 beta decays. Wait a second, let me think about it. I think I'm correct. If I had done some mistakes in overall calculating it, please don't mind it. Okay, so this is about the actinium series. Now, so this is about the actinium. This is about some of the not some but 4 natural radioactive series. Let's talk about the successive radioactive transformations. That means each of the steps, how each of the steps are involved in this series. Okay, so let's take some series. Let's say the uranium series, and let's see what are the successive products also. And let's assume, and let's examine where the positions where the alpha decays and these beta decays are actually happening. Okay, so it'll be quite interesting. So let's do that. Okay, so let's see the uranium series. Now it had got 14 steps, and In each step, either the alpha ray or beta ray or gamma ray is decayed. Okay, so let's see each of these steps. So first of all, we have uranium 238, and its size is, so we have got, so its size is so heavy, so it would like to do some alpha decay. So if it reduces alpha, so after alpha decay, what would we get? Now alpha means helium nucleus. So if it's alpha decay, then we would get something that would result into 234 of the thorium. So 230 thorium and 92 minus is 90. So we would get 234 thorium. What after this? So after getting this uranium, from uranium we get thorium by alpha decay, and then after, if you see, if you see this thorium, you would notice some issue with it, and that is it has large number of, or it has a very large difference in between the neutron number and proton number, because you can see it's not even 100 and it's 234, so there is a margin of about 144. Okay, so it has number of neutrons is 134, and number of proton is just 90. So there's a large difference in between them, and as a result of which, it would like to convert some of its neutron to proton, and in that process, the beta minus decay would happen, and as a result of which, we get beta minus decay. So that would result into a gain of one proton, and the atomic weight won't change. Okay, so we got 23491, and that is protactinium. So if you say this, so it will be 320, yes, 334 and 91, that is protactinium. I think P. Yes, I think it's yes P. Now what would we get? So after this, we get, okay. So actually the protactinium stand, the symbol for protactinium is A, and this is our. Now I think I should write the name of it. So it's protactinium. We got it by beta minus decay from thorium 234. Now what after this? Now you can see this protactinium is still a very in protactinium also there is a very large difference in the number of protons and number of neutrons. That means it would again like to uh, do a beta minus decay, and it would result into 92 of the 92 protons, and 92 protons is uranium, and uranium 234 is obtained. Okay, this is what we get. So up to now we have got, again here also we have got beta minus decay. So up to now we have got 4 steps. Now let's see after this what would happen after this. So if you see this uranium 234, now uranium 234 would likely perform alpha decay, and an alpha decay would result into 230. So 230, and what is the number of the protons? The proton number would decrease by 2. That would be was 90. So 90 means thorium. So again we get 230 thorium. Okay. Again, okay. So we got 230 thorium. Now I think I should rest it here and use the next board. So let's do that. Now this thorium would likely do an alpha decay, which would result into 226, and the number of protons would decrease to 88, and this is radon. So this is radium. So we would get radium 226, and this is very famous. This is a very famous reaction studied by very famous scientist Marie Curie. It is studied famously by Marie Curie. Okay, that's the fact. Now, after this, what we would like to see is how would you like to proceed with the radium? Now, this radium, if you see the radium, if you understand the property of it, it would again likely perform a alpha decay, and this alpha decay would result into 224 and 86, and this is radon. This is the radon that I was talking about. So this radon, and this is a heavy radioactive gas that can seep into the basements. Okay, so this is about the this is a curious fact about radium to radon. So I think I should write it. It's a radium, but it's a radon. Now, what after this? Now, this radon, we have 86, and so we have 82 in the lead, which is a stable product. So we would likely go up to that. It means we also we are now interested to reduce that proton number, and for that, for reducing a proton number, only one of the a thing is possible, and that is to do alpha decay. So let's say it decays and alpha, it does alpha decay now, then that would give us 200 and 200 and which means 208, no, 218, 218, and number would be 884, and this is something that we call as polonium. After getting this polonium, now this is what the reaction look like from radon to polonium. After this, we have got 218, and it means you might think that one of the alpha decay is enough to get that in product, right? So let's do that. So again, this would result. Actually, radon is written by Rn. Okay, so now if it does alpha decay again, it would get PV, and it is 200 and what? Wait a second. Let's write 82 of PV. And what about the atomic number? So atomic mass. Atomic mass would be 208.14. So we have got an isotope of lead, but not the stable product quite yet. Now, what do you think would need to do to reduce this number? And for that, what you need to do is let's say we have to do a beta minus decay, and that would result into, so let's suppose we have to do a beta minus decay, and it will result into 83. And we already know the product 83. And what is it? I think the product 83 is polonium. No, not polonium, but bismuth. Bismuth 214. Now it was recently found that bismuth is quite not stable. Then what we get is you convert. Now this bismuth is converted into polonium by again beta decay, beta minus decay, and beta minus decay would cause it to be 84, and 84 means polonium 214. So we have got this. Okay, so we have got polonium, and after this polonium, what we would get is it would not, actually it would, let's not give us this stable product yet, but it would go into alpha decay, and it would result into 200 and 210 and 82, and 82 means lead. We have got another isotope of lead, and then after lead, after getting the lead to 110, this would result into this 210 lead. Now these are the corresponding steps. First of all, this bleed 82 210 would do a beta decay to get a bismuth 210, and that would again do a beta minus decay, and that would give us 210 polonium 84, And again, this polonium 210 polonium 84 would do alpha decay to get this stable product or the end product lead 206 82. So after getting this or after understanding what are the steps, what are the steps, now you would be wondered and you would be wondering how do we remember all the steps. And for that, let's see something. So for that, let's try to visualize what's going on with these reactions. So we firstly had uranium 238 92. So 238 92 would be here, and it would lastly result to 206 lead 82. That means we would get 206. This is the 206. This is 206, and 82 would be like here. So this is our stable product. So okay, this is our stable product. Now we have to understand how this goes from this to this. Now for that, we would like to plot all these intermediate steps, and let's do that. So first of all, this uranium 238 would decrease up to thorium 234. So thorium 234 would be thorium. What is the value for thorium? Thorium, what is the atomic number for thorium? It is 88. I think so. No, it's 90. So let's, okay, yes, it is 90. So 90 to 34. 90 to 34 would be 90. What is 234? Is 234? 234 is 31, 32, 33, 34. Okay, so the first step would decrease it from from here to here. This is the first decrease. Okay, what after this? Now, what it does, it doesn't change the weight, rather it changes its the number of protons. For that, it does a beta decay, and that would lead us to uh, 81. So 81 would be, sorry, 91. 91 would be somewhere like here. 91. So 91 for 91 and 234, we would get point here. So we have got these three reactions, these three steps, and after that again, it doesn't change its atomic mass, rather it changes atomic number. It means it does a beta decay, and this beta decay would result uh, into Pa 234. So 234, but the value is 93, right? 92. So 92, but 234. So that means we have got a point here. Okay, what after this? Now after this, it would like to change its value from 234. So I have got 234, right? So I have got 234, 234 and 92. Now this is another isotope of uranium. That's why this isotope of uranium would change its value to thorium again, and the thorium would get 232 atomic mass, and 90 to be its atomic number. So we would get a point which is 232. Where is 232? 31, 32. So 232 would be, but the atomic number doesn't change. I think we'll get a point here. So we get this line. Now after that, this thorium 230, yes, the 230 would do an alpha decay. So actually, yes, this is thorium. Now this is 230 or 232. Okay, what it does is, wait a second. Okay, if it does alpha decay, then it will be 330 to 30. So I think we have to write 230 instead of 232. That means we have got a value which I think which is here. So that means here there is a step, there is a steep decrease. Okay, okay, it's good. So what after this? After this, it will again like to uh, decrease its atomic mass by releasing its alpha ray. So this would again do alpha decay, and it would give us 88 to 30, no, not 30, but 226. And this is radium. It is radium. So radium would be 226. So with 226, I think here. So 226 would be 226. Okay. Now what is the atomic number? Atomic number is 88, somewhere like here. So we get a value somewhere like here, and again decrease in a step line. Okay. And after that, it would again do a radioactive, sorry, not alpha decay, and it would alpha. So after that alpha decay, it would be 86. Now 86 is right on, right? So 222, 222 is this. This is 222 and 80, 86. So this is 86. We would get a value here. So we would get a line here, and after that again, it would do a radioactive, not radioactive, but it would do a alpha decay, and which would result into 218 radium 84, not so 84. Now 84 means that's a radium. That's a 84 means, wait a second, I think, yep, we have got radium. Now radium to radon. Yes, 222, 218. Now when I say about 218, so it's actually polonium. So we would get polonium 200, 218, 84. So 84, 84 and 218. So 218 means 20, 19. This is the time. This is the point. So we would get, okay, I think I should have used yellow, and I would get a point here. We're getting to that stable product, but there is some difference up to now. Now what after this? After reaching this polonium, it would again do a radioactive alpha decay, and this alpha decay would result into 214, 214 and 82. Now 82 we know is lead, so that's why we get 82, but not 206, but rather 214. So 214 is this one. So this is the point. Now what after this? Now we cannot do a linear jump from like this, because it would exceed, or it would uh, exceed the value of 82. Uh, it will go there, so it cannot go there, so it would rather go there and there. So it means we have to stop our alpha decays, and we'd focus on the beta decays. So if this 214 82 BB do uh, a beta decay, beta minus decay, it would gain a number. It would be 83, and this 83 is actually bismuth, right? Yes, bismuth. Now it would get bismuth, and after getting to that bismuth, it would again do a beta minus decay. It would give us 84, and 84 is the polonium. Okay, we get polonium. Now 26. Wait a second. So after this, yep. So I think we would be interested. Yes. So what it does is it goes to 83. So this is 83 by beta decay, beta minus decay. 83 mass is same. So we get a value here. Yep. Then after it would go again by increasing its number by beta minus decay, and it would get to here. After getting this, it would change, or it would, yes, it would what? It would do a beta, sorry, alpha decay. Now what would do? What would 214 83 bismuth 84, right? So 84 means polonium would do is that it would do alpha decay. So alpha decay would result into 82, 82, but the value of the atomic mass would be 212. So it would get 212. So this is the value. So 212, and this is the here. Now again cannot go there. So now it again have to do some beta minus decays, and if it does a beta minus decay,
It go here. That is 200. 214 is 214 has been changed to 212. 212 and it is 80. It had 80, 82. 82 is lead. Now it will again go to 83. PV 230. It will again go to 212. Again 212. It will be 84. It is smooth and it will again go to bismuth again. Now the bismuth 200, 212, 83 would change into 84, 212, and that would give us 84. What is that for? Polonium, and this will again do alpha decay, and this alpha decay would result into 200 and what? 200, 208, 208 what? Is it 208? Yes, it is 208. What? 208 PB 82. And is this the stable thing? Let me see that. Is it the stable thing? So after this, okay, so we would get 210. Okay, so what it does is it gets to 210 after 212. Okay, so we have got 212. So this is 212, okay, 212, and it goes back by giving okay, so we have got 210. And after this, what it does is it reduces further to 208. So 208. So we'd get 208. What is it? What is 208? So this is 208, and it would be 81. Okay, 81. So we would get a graph which looks like this. And then after, what it does is it changes by gaining beta minus by getting involved into a beta minus decay, and it would increase its value from 208, and after that, actually, not 208 but rather 200, 200 210, and after this 210, one alpha decay would result it uh, to its value here, and after some beta minus decays, it ultimately get to that value of 82 and 206. That is the stable product. So if you want to see this perfectly, now it looks like this. Okay, so I think, yep, if you want to see this, it looks something like this. Okay, now if you remember this, then it will be very easy for you to understand and to remember this uranium series. Now if you see other series and the paths of other series, it would be a little bit different. So for example, if you want to see the thorium 232 decay series, it would look something like this. So even though we can understand how much of the alpha decays has been happening on the basis of this graph, but we can see a little deformities from the previous one of uranium series that we have seen. So this is about uranium series and other series, and this is about how you can visualize series. I think I was able to make you understand this.